So in this video, we will extend our stochastic integration theory beyond the Brownian motion. So far we've talked about integral of processes against the Brownian, and they are really limits of martingale transform of increments of the Brownian. Now, we would like to have a similar integration theory for more general stochastic processes than just a plain Brownian motion. And in the same way as we had Ito formula as the fundamental theorem of calculus adapted to integration against the Brownian, we would like a version of Ito formula adapted to integration against a more general process. Because the processes we will be looking at are built from the Brownian and deterministic integration, we will find that getting a Ito formula for a more general stochastic integration theory is really the same question as getting a version of the chain rule for the Ito calculus. So let's have a look at the class of processes we would like to treat and start looking at what a chain rule might look like. So we'll be looking at processes that are solution of such a stochastic differential equation. So we've already seen an example of that in the case where A and B are constant, and really our process is just a multiple of time, so a certain deterministic function of time, and a scalar multiple of the Brownian. Now we want to generalize that in such a way that we allow the coefficient in front of the Brownian to be itself a process, and same thing in terms of the deterministic part of the integral. So we want A and B to be adapted processes, and then we would like to be able to integrate certain adapted processes, and we would like to integrate them in the obvious way, somehow really interpreting this stochastic differential equation in an integrated sense, so defining the integral of f against dxt as the, for every omega in your probability space, as this integral, which is a Riemann integral or a Lebesgue integral, as long as this is in L1, plus this integral, which really is interpreted in the Ito sense, which will make sense as long as this process here is in L2 log. So these are really the conditions to make sense of the right-hand side, right? I want f times A to be in L1 for almost all omega, and I want f times B as a process to be in L2 log. So what we will mean by the integral of a process against the integral of a process f against a process xt, where xt is a solution of such a differential equation, is by definition this integral. So this combination of a Lebesgue integral and an Ito integral. That makes sense. Now that extends our integration theory beyond the Brownian, right? The case of just the Brownian would be if B was 1 and A was 0, to a much larger class of processes, anything of this form. Now this will be very helpful down the track, because this class of processes is actually quite large, and they will be really the type of processes we need to look at in our applications to finance in particular. So typically in finance, you would have here something that is a quantity of cash, so something that will vary in a deterministic manner based on an interest rate, and here you would have the quantity of a certain stock which behaves in a stochastic manner. So really what we would have here is the value of a certain portfolio made of a certain amount of cash and a certain amount of stock. Right, but beyond those applications, what we get here is a much wider class of processes built from linear combination of, well, deterministic processes that we already understand very well, so standard calculus, and our building block for stochastic processes, which is the Brownian motion. Okay, so the question we're asking is that, right, now, given such a process, xt, what if I form a function of time in that process? Do I have a Ito formula that would allow me to get a stochastic differential equation for a function of xt, or even a function of t and xt, in terms of dt, dbt, or dxt. Now, in order to understand that, so you think of xt itself as a function of dt and, well, of t and bt, and so you're really looking at a function of t and bt. So trying to understand what sort of differential equation a function of t and bt satisfy is a chain rule type question, right? You're taking a function of a function and you want to describe the derivative of that based on the derivative of what's inside. So in order to get a feeling for what such a chain rule might look like, or put in a different way, what the Ito formula should become if you replace the plain Brownian bt by such an xt, we're going to look at an example. We're going to look at the simplest version of a process like this one that mixes a deterministic component and a Brownian motion. So we're going to look at the case where we have two numbers, mu and sigma, and we form a process of the form mu t plus sigma b of t. So some linear deterministic growth plus a noise, which is a multiple of the Brownian. So we're looking at the case where a and b are constant processes. Now, let's try to find out what d of f of xt is in this case, and that will give you the right intuition for understanding, more generally speaking, what the stochastic chain rule should look like. So let's get through this example. Okay, so in this example, I have a process which is of the form mu t plus sigma bt. And then I have a function which is, say, c1 in the time variable and c2 in the x variable. And I want to understand what is d of f t xt, right? Now, I want to use Ito formula adapted to the Brownian in order to deduce an Ito formula for that process. So what I can do is that I can define a new function, gtx, to be f of t and mu t plus sigma x for all t and for all x, right? If I do that, I'm going to have that gtbt is ftxt for all t. So dftxt, which is what I'm interested in, the stochastic differential equation that is function of time and the process xt satisfy, is really just d of gtbt. But for that, I can apply Ito formula. And Ito's formula tell me that this is equal to dx of gtbt times dbt plus dt of gtbt times dt plus the correction term, which is 1/2 d square x of gtbt dt. Well, that's exactly Ito's formula for the function g. Now, how do I relate the function g to the function f and the dbt and the dt to dxt? Well, dt of gtx is equal to what? It's equal to dt of f, t mu t plus sigma x, plus dx of t ft mu t plus sigma x times the derivative of this in t, which is mu, right? And now that's just by the standard deterministic chain rule. And so what can I say about dx of gtx in the same way? That is, well, sigma dx of f t mu t plus sigma x. And then what can I say about the x squared of gtx? This is sigma squared dx of f t mu t plus sigma x. All right, all of that is for every t and for every x. Okay, so let's plug that back in. I get dftxt equal sigma dx of ftxt times dbt, okay, plus the dt part, which has a mu dx ftxt dt, plus a dt ftxt, and then plus 1/2 of the dx squared part, which has a sigma squared, and then dx ftxt dt. So now you have sigma dbt here and mu dt there. When you sum them, you get dxt. So what we have is dx ftxt dxt plus dt ftxt dt plus 1/2 of sigma squared dx ftxt dt. So this looks very much like Ito formula, right? If xt was just bt, then we would get this term, we would get this term, and the only difference really is here we wouldn't have the sigma squared, right? And of course, because if xt was bt, this would correspond to sigma equal to 1. So this sort of suggests what the correction term should be, right? The correction term picks up what was in front of the Brownian in the definition of xt, and that being squared. Now, really, what we have seen here on a simple concrete example for which we can compute the dftxt just using the Ito formula for a function of t and bt is part of a more general theory of stochastic chain rule. So we know how to get an Ito formula for a process that satisfies a SDE of the form dxt equal a dt plus b dbt. We've just understood that in the case where a and b are constant. If a and b are not constant, before we go any further, we need to make sure that we've put appropriate assumptions on a and b such that this SDE has a solution. Now, what does the solution of that SDE look like? Well, remember that this SDE notation is just a notation. What we mean by this SDE is really this integrated version. So xt is x naught plus the integral of a in the Lebesgue sense plus the integral of b in the Ito sense. So what do we need for this to make sense? Well, we need to integrate in the Lebesgue sense something that is Lebesgue integrable. And we do that for every value or almost every value of the probability parameter omega. So we need to make sure that almost surely a is integrable in the time variable. So this is the condition we need to put on a. And here, well, what do we need to have the Ito integral well defined? We've got it well defined for an L2 log process. So what we would need is an L2 log condition on B. So if A is almost surely L1 in time and B is in L2 log, then we call this process, which is the solution, put in a different way of this SDE, as we call that a standard process. Now, what we want is an Ito formula for the stochastic integration against any standard process, with the standard Ito formula being the special case where a equals 0 and b is equal to 1. So this is given in theorem 5.12, and the formula is very similar to what we had for the Ito formula. We get this term, which is really the analog of what we would get in deterministic calculus, right? You could rewrite that as gradient of ftxt dot the vector dt dxt, right? I mean, this is purely a notation, of course, because this, neither dt nor dxt have a meaning in themselves, let alone putting them in a vector and giving a meaning to that. But nevertheless, this is, at least formally what you would expect from deterministic calculus. And then we have the correction term, which was 1/2 of the second derivative in x of ft bt times dt in the case of the Brownian. And here, well, instead of dt, we've written dxt dot dxt. Right? And again, this is purely a notation, but this is a notation that gives you the right intuition. This is, the first order term in a Taylor formula, and this is the second order term in the Taylor formula, so it has the variation of x squared. And what do we mean by this notation? Well, we mean b squared times dt. That would be that by definition. That is the way I define dxt.dxt. If dxt satisfies this equation, then I denote by dxt.dxt b squared times dt. So in an integrated form, what I would mean by the integral of that, it would be the integral of dx squared ft xt times b squared dt. So it will be once again a Lebesgue integral. Now, if if a is 0 and b is 1, then I should get standard Ito formula. And I do, because then my dxt is just, if b is 1, dt. Now, what about the case where a is constant and b is constant? That's the case we treated in the example a minute ago. Well, then in that case, b is constant equal to sigma. And so I get sigma squared dt here. And so the correction term I'm getting is exactly what I found just by computing and applying the standard Ito formula in the example. But more generally speaking, this is what you get. If you repeat the proof of Ito formula, but you replace the Brownian by a more general process of this form, really the entire proof goes through. The only thing that changes is the hard part of the proof, the part where we deal with the quadratic variation of the Brownian. So I recommend doing that as an exercise. Go back to the proof of Ito, replace all of the bt by xt's of that form, and you will see that nothing really changes. I mean, or more precisely, you can apply all of the things you know from bt plus the things you know from standard integration theory, Lebesgue integration theory, and you will get the formula we have here, except at some point you will need a replacement for this fact here. So this fact here was critical in the proof of Ito formula. This is how the correction term compared to deterministic calculus pops up, right? And this comes from the fact that this sum of increments of the Brownian square tends to t as n goes to infinity. So in order to prove 5.11, all you have to do really is understand what the limits of the quadratic variation of such a standard process is. And that's the subject of the next section.